Welcome to this math lesson on integration techniques. In calculus, integration is a fundamental operation that allows us to find areas, volumes, and solve many other problems. Today, we'll explore two essential integration methods, basic approaches including substitution and integration by parts. We'll walk through each method step by step with clear examples. Let's start with the most basic approach, direct antiderivatives. Some functions have well-known antiderivatives that we can apply directly. For example, the integral of x raised to the power n equals x raised to the power n plus 1 divided by n plus 1 plus c, as long as n is not equal to -1. The integral of e to the x equals e to the x plus c. The integral of cosine of x equals sine of x plus c. And the integral of sine of x equals negative cosine of x plus c. Let's see a concrete example of using direct antiderivatives. Example 1. Compute the integral of quantity 3x squared minus 5 dx. We can apply the linearity property of integrals to split this into the integral of 3x squared dx minus the integral of 5 dx. For the first part, we have 3 times the integral of x squared dx. Using our power rule with n equals 2, we get 3 times x cubed over 3, which simplifies to x cubed. For the second part, the integral of 5 dx is just 5x. Combining these terms, our final answer is x cubed minus 5x plus c. Next, let's explore a more advanced approach, the substitution method, also known as u-substitution. This method is useful when an integral contains a composite function and its derivative. The steps for substitution are: Step 1. Identify u equals g of x so that du equals g prime of x dx. Step 2. Rewrite the integral in terms of u. Step 3. Integrate with respect to u. Step 4. Substitute back u equals g of x to get the final answer. Let's see an example of substitution. Example 2. Compute the integral of x times cosine of x squared dx. Step 1. We identify that u equals x squared would be a good substitution. Then du equals 2x dx, which means x dx equals 1/2 du. Step 2. We substitute these into our integral. The integral becomes the integral of cosine of u times 1/2 du, which equals 1/2 times the integral of cosine of u du. Step 3. We integrate with respect to u. 1/2 times the integral of cosine of u du equals 1/2 times sine of u plus c. Step 4. We substitute back u equals x squared. Our final answer is 1/2 times sine of x squared plus c. Now, let's move on to our second major technique, integration by parts. Integration by parts is based on the product rule from differentiation. If you recall, the product rule states that the derivative of a product of two functions u of x and v of x equals u prime of x times v of x plus u of x times v prime of x. If we rearrange and integrate both sides, we get the integration by parts formula. The integral of u times dv equals u times v minus the integral of v times du. When should you use integration by parts? Choose u to be the factor that becomes simpler when differentiated, and dv to be the rest of the expression times dx. A helpful acronym to remember which functions to choose as u is Lie8, logarithmic, inverse trigonometric, algebraic, trigonometric, and exponential. Functions earlier in this list are better candidates for you. Let's see integration by parts in action with an example. Example 3. Compute the integral of x times e to the x dx. Step 1. We need to choose u and dv. Following our Lie8 acronym, x is algebraic and e to the x is exponential, so x should be u. So we choose u equals x, which means du equals dx. And we choose dv equals e to the x dx, which means v equals e to the x. Step 2. We apply the integration by parts formula. The integral of x times e to the x dx equals u times v minus the integral of v times du. That's x times e to the x minus the integral of e to the x times dx. Step 3. The integral of e to the x dx is simply e to the x. Step 4. Putting it all together, we get x times e to the x minus e to the x plus c, which can be written as e to the x times quantity x minus 1 plus c. For more complex integration by parts problems that require repeated application of the technique, we can use the tabular method. Let's see this with an example, the integral of x squared times e to the x dx. we set up a table with derivatives of u in the left column and integrals of dv in the right column. For u, we start with x squared, then take successive derivatives until we reach 0. For dv, we start with e to the x dx, then take successive antiderivatives. To calculate the integral, we pair terms diagonally with alternating signs. We multiply the first row of u with the first row of v, then subtract the product of the second row of u with the second row of v, and so on. This gives us x squared times e to the x minus 2x times e to the x plus 2 times e to the x plus c. Factoring out e to the x, we get e to the x times quantity x squared minus 2x plus 2 plus c. Let's summarize what we've learned about integration techniques. For basic approaches, we use direct antiderivatives with known formulas, substitution when we see a composite function and its derivative for integration by parts, we use the formula. Integral of u times dv equals u times v minus the integral of v times du. The tabular method for repeated applications, remember these guidelines for choosing the right method. If the integral is a basic function or a sum of basic functions, use direct antiderivatives. If you see a composite function and its derivative, like sine of x squared times x, try substitution. If you have a product of functions like x times e to the x, and one function gets simpler when differentiated, use integration by parts. Practice is key to mastering these techniques. The more integrals you solve, the better you'll become at recognizing which method to apply. Thanks for watching, and happy integrating!